We start today by reviewing where we were at the end of last class. And at the end of last class, we were looking at dilutions. And if you recall, dilution is merely just the process of adding water to an existing solution. And when we add that water, we will decrease the concentration because even though we are increasing the volume, the amount of solute hasn't changed. And so we ended by looking at this so-called dilution equation. And this dilution equation, what we see is that we can directly relate the concentration and volumes of our initial solution with our final solution after we've done the dilution. And we did an example problem of this. And one thing I wanted to make really, really clear is that your book presents these two equations as being somehow fundamentally different from each other. They're not. They are basically the same equation. And so even though we are doing a molarity dilution here, we're going to use the same equation. C1 times V1 is equal to C2 times V2. And we end up getting, in that case, 3 molar as a result. So before we move off of dilution, I want to take a couple of minutes and just do some more practice problems just to show how we use this equation and what kinds of problems it can solve. So question like this: what volume of a 2% mass by volume hydrochloric acid solution can be prepared by diluting 25 milliliters of a 14% mass by volume solution? And so again, the key to these kinds of questions is identifying what our terms are. So we have here 25 milliliters, that sounds like a volume. And 14%, that sounds like a concentration. And since this is the more concentrated solution, this is solution number 1. And what we know about solution number 2 is just this. This is its concentration. So that's our C2. So using our dilution equation, C1 times V1 is equal to C2 times V2. Our initial concentration is 14.0%. Our initial volume is 25 milliliters. Our final concentration is 2%. And we don't know what V2 is. Now, again, the beauty of this particular equation is that it is completely indifferent to what the units are, so long as they are the same. And so this becomes a matter of simple algebra to solve. I'm going to divide each side by the 2%. Percents cancel, and I'm left with milliliters. I just need to figure out what the value is. 14 times 25 divided by 2 would give us 175 milliliters as our second volume. So in this particular case, we were trying to figure out how much solution we would end up making to get this particular type. The previous one, it was all about how much of the initial solution we would need to measure out. So lots of different ways that we can go about doing this. Our next study problem looks at a similar kind of issue, only we are looking at the concentration of the final solution instead of the volume of the final solution. Again, diluting 10 milliliters of 9%. These are our initial conditions. 60 milliliters is our final volume. C1V1 is equal to C2V2. And C1 was 9%. V1 is 10 milliliters. C2, we don't know. V2, 60 milliliters. Divide each side by 60. The 60 milliliters will cancel out. The milliliter units will cancel out. And so all that is left is the 9 times the 10 divided by the 60. So 9 times 10 divided by 60 would give us 1.50. Again, using our rule of thumb, every value we've been given has had 3 digits in it. So we're going to round our answer to 3 digits as well to maintain that consistency. The unit here is percent. In this case, it would be percent mass by volume. Not that it really matters. And that would be the final concentration of this solution. All right, last study problem is regarding molarity. With molarity, we're looking at diluting 0.180 liters of a 600 mole or a 0.6 molar solution of nitric acid to 0.540 liters. Again, we use the same equation, C1V1 is equal to C2V2. So long as our units match, we can use this equation for any scenario, any concentration, any volume unit, so long as the units match up. So the fact that we have liters here instead of milliliters, it doesn't matter. We're going to get the same thing regardless. Now it's just a matter of identifying, this case, it's our initial condition and our final condition, the V2. So our initial concentration, 0.600 molar. Our volume is 0.180 liters. Our concentration, we don't know. Volume, 0.540 liters. Same as before, to isolate C2, we would need to divide each side by 0.540 liters. That would get the whole thing to cancel out other than C2 on the right-hand side. That would cancel out the liters on the left-hand side. We would end up with 0.6 times 0.18 divided by 0.54, 0.200 molar as our final concentration. So that's dilution in a nutshell. Really easy equation to use. The trickiest part about it, honestly, is just identifying which components are the initial and which are the final. And for that, you want to just look for keywords like diluting versus diluted to, because that kind of gives us the difference between them. So again, each one of these examples, we were diluting something, which means that those conditions we were given are initial conditions. In this first one, we were given a, again, similar kind of scenario where we were diluted to a final volume of 1 liter. What we can understand, though, is it could go in the opposite direction as well, where we know what we're trying to make, and then we have to figure out how to make it. So, starting with the final conditions and rolling back, usually to the initial volume. That's usually what we're trying to do in that kind of scenario. Is we have a stock solution, we want to turn it into a diluted solution with a particular concentration and a particular amount. And so we need to figure out how much to measure out to do that. So that's the end of section 5. In section 6, which is the last section of this chapter, what we're going to look at are some general properties of solutions. And in particular, we're going to look at some cases where, where solution type and solution concentration can have a significant impact on your body chemistry. And we're also going to look at some examples of solutions that aren't actually solutions at all, but look like solutions. And we're going to talk about colloids and suspensions in those cases. So, solutions. We know solutions are transparent. Another word for that is clear. We can see through them. We also know that they don't separate. I can't get my solution of iced tea to separate into pure water and the tea leaves again. It doesn't work like that. It's one whole solution. And we also know that they contain small particles that can't be filtered and would pass through certain kinds of semi-permeable membranes. And so the key idea there is if we had a solution, so let's say we have a saltwater solution, if we were to pour that saltwater solution through a funnel and into a filter paper, the filter paper is not going to separate the salt from the water. If it did, then we wouldn't be talking about a solution. We'd be talking about a heterogeneous mixture. And again, the difference between the two is uniformity. So that's what solutions are. Now, when we get into colloids, in a lot of ways, colloids have some similar kinds of properties to what we would think of as solutions. The particles are a little bit bigger. They have a uniformity of appearance. So in a lot of ways, they look like solutions. And if we try to filter them out, we can't filter out the colloids. But they can be separated by separate semi-permeable membranes. And so this is where we're going to get into a discussion more along the lines of, reverse osmosis filtration, or osmotic pressure, or other separation techniques of this kind, dialysis. And so that's one way we can tell a solution from a colloid is just looking at that. So what are some examples of colloids? How do we know? And so when we talk about colloids, we can't really talk about them in terms of solution, solute versus solvent, because they really aren't making a solution entirely. What we're talking about is the dispersed substance in the dispersing medium. Now, if we want to use such terms, the dispersed substance, it's not actually a solute, but it's, in terms that we can understand, it is as close to solute as what we would think. And the dispersing medium, this would be the equivalent of something like a solvent. So you look at fog. Fog is a mixture of liquid and gas. Gas is the solvent. It isn't present in the greatest amount. The liquid is kind of dispersed throughout it. It appears to be uniform in its appearance. It's not necessarily transparent. It appears uniform, but it isn't actually a solution. With dust or smoke, we're getting solid particles very finely dispersed through a gas. You look at things like shaving cream or soap suds. You've got liquid carrying this gaseous substance inside of it, and you're getting a liquid-like kind of appearance that has been frothed up. You look at something like milk. Milk is an example of a colloid. And the reason it appears so uniform is because it's been homogenized. We have basically broken down most of the fat globules inside of the milk to a small enough size that they will kind of just remain floating around in that liquid medium. Not really a solid, not really a true liquid solution, because anyone that knows milk will know that if you let milk sit out long enough, it will start to separate, because it'll start to the fat parts will start to separate from the aqueous parts. And we know that's not truly homogeneous in its appearance. It does have some inconsistencies. Cheese and butter, again, you can see we got a solid with some liquid components kind of spread throughout. Your blood plasma, gelatin, you've got liquid components in your blood and some solid pieces kind of mixed in throughout. Suspensions, on the other hand, these are heterogeneous. They are non-uniform. You can make a suspension by taking some dirt and mixing it into water. And when you do that and you stir it up, initially speaking, it's going to make this brown, muddy stuff. Take a scoop out of the Wabash River, you're going to find the same thing. It's going to look kind of uniform, at least in the liquid phase. You let it sit there long enough, the really large particles that are in there will start to settle down to the bottom. And because of this, we don't really have a uniformity here at all. It's very, very temporary. And that's what makes it different from a colloid. A colloid is a lot more permanent in kind of the way that those particles are dispersed. Suspensions, the particles are so big, they settle out. We can easily filter them. The only way that they stay kind of in that uniform appearance, sort of, is if they're continuously stirred. And so comparing all of these against each other, what we see is that it basically goes from a big to small kind of ranking for what the thing that is dissolved is. So the bigger the particles are, the more likely they are to be a suspension, and the more likely they will be to be filtered. As you go to solution, the particles are so small that they don't settle, and you cannot filter them in really any kind of way meaningfully. And with colloids, it's kind of in the middle. Colloids can't be filtered. You can't filter your milk. But you introduce a different kind of semi-permeable membrane, and now you have the ability to filter out the components from each other. So slight differences in wording there, but important things to know. So, here's kind of an example. Let's say we have a scenario where we have all three present at the same time. We have a colloid, we have a solution, and we have a suspension. What we're going to see is that if they were all just in an open beaker, any kind of container together, the suspension on sitting would settle. And so the solid components would just sit at the bottom here and would not mix up unless we did the mixing ourselves. If we ran this substance through a filter, the filter would catch the suspension particles, but you can see that the solution particles here in yellow and the colloid particles here in green they would pass through the filter paper and end up in the purified water here at the bottom. Now, this picture is a little bit hard to see what's happening, but when you see it in lab, it'll make a little bit more sense. This is a semi-permeable membrane bag. And what you'll find in the semi-permeable membrane bag is you've got what looks like a piece of plastic, but actually has very, very, very fine holes in it. And what you'll see is that the holes are so fine that if I were to put a solution inside this bag, so let's say we took this solution, this liquid mixture out of this beaker, and we poured it into this membrane bag. And then we put the membrane bag inside of just a normal beaker. Well, what would happen is the water would naturally flow out of the membrane bag, because even though it has, small microscopic holes in it, the water molecules are small enough they will leak through those holes. Also leaking through those holes would be any particles involved in the solution. Because again, they're small enough that they can fit through those tiny microscopic holes. Colloid particles, however, notice how they are still in the bag. Suspension particles, notice how they are still in the bag also. So that's kind of the difference between them. It's really a matter of particle size. And filter paper, generally speaking, is not fine enough to really show that difference in size. The holes in filter paper that allow the water and the solutes to pass through are also big enough to allow small colloid particles to go through as well. Won't let through big particles like dirt or sand or other things, but would let those smaller colloid molecules through. But a semi-permeable membrane, sometimes we refer to these as dialysis bags. These are so small that we can get nothing to pass through them other than water and the particles, the solution particles, the solute. So just to kind of review here, a mixture that has solute particles that do not settle out and are too large to pass through the membrane, this would be an example of a colloid. Because it does not settle out, so that means that it's not a suspension. But it also doesn't pass through the membrane, so that means it's not a solution. So colloid would be the correct answer there. All right, let's talk about another common property of solutions, osmosis. So here's another example of where we have a semi-permeable membrane. Now, semi-permeable membranes come in a variety of different sizes and different particle sizes. And so in osmosis, what we see is that we have a relatively fine semi-permeable membrane that only allows water to pass through it. So unlike the dialysis bag that we saw in the previous example where solute particles could travel through it, this one is so fine, so small that only water can pass through it. And so what we see in osmosis is just this tendency that water molecules will flow from an area of high concentration to low concentration. So if I have two solutions separated by that semi-permeable membrane, the solution that has a more dilute concentration will send some of its water across the membrane to the more concentrated side in an attempt to try to get them to balance out each other and end up at the same concentration. So in this particular example, we have a more concentrated sucrose solution over here and pure water over here. What's going to happen is the water is going to travel across the membrane from the low sucrose side, the high sucrose side, in an attempt to get them to balance out with each other. Now, since there is no sucrose on the low sucrose side, we're never going to get the concentrations to be exactly equal. What will eventually happen is basically the osmotic flow is going to run into a different force, gravity, pushing down on the mixtures, and the force of osmosis is going to match the force of gravity, and that's going to be kind of when the whole process stops. But assuming that you actually do have the ability to get both on the same side, that is what would ultimately happen. And so osmotic pressure is a phenomenon that we talk about to describe exactly what I was just saying. So how much pressure do I have to apply to the one side of the vessel to get the water to stop flowing across? So it's flowing across, flowing across, flowing across, trying to get these pressures to equalize. How much pressure do I have to push on this side to stop that water from going across and just stay where it is? That's osmotic pressure. Now, osmotic pressure is related to a couple of factors, but key among those factors is the concentration of the solution. The more concentrated this solution is, the more water is going to have to flow across to try to get it to balance out. The more pressure we're going to have to exert to stop that flow from occurring in the first place. Where this becomes useful for us, or at least where a common application of this is, if we know the osmotic pressure of a particular solution, well, what if we don't want to equalize the pressures? What if we don't want the water to dilute, but rather we want to purify the water? So reverse osmosis filtration works on that exact principle. The exact principle of, I've got some dirty water over here, and I've got some clean water over here. If I just put a membrane between them, the water would flow from the clean side to the dirty side. We don't want that. We want water to flow from the dirty side to the clean side. How do we do that? Well, we've got to put enough pressure on this side, not just to stop the flow, but to actually reverse the flow so that it actually goes from the dirty side to the clean side. So the more concentrated, the more dirty the dirty water is, the greater the pressure is that we're going to have to exert to get to this reverse osmosis. Now, reverse osmosis has a lot of different applications. We see it in a lot of water purification kinds of projects. A number of different municipal water plants utilize reverse osmosis to clean out any impurities that might be in the water based on the source of the water or the condition of the pipes or whatever the case may be. In more remote areas where maybe freshwater access is a bit of a concern, reverse osmosis can be used in the process for desalination, where we can remove the salt from salt water by pumping it through these reverse osmosis chambers and gradually taking the salt out of it. Now, doing so requires quite a bit of energy, but in those kinds of scenarios, it might be the best form of getting what you need and what you want, because the other option is to distill it, to basically heat it until it boils and then let the boiled water collect and cool and then treat it, that requires a lot of energy too. But in those parts of the world where fresh water is not an option or not easily acquired, yeah, that might be their best option is desalination. Now we get into some body chemistry stuff. With this idea of osmosis in mind, we need to think about how your body works. And so just take, for example, your blood. Your blood is the superhighway of your body. It's what your body uses to transport materials and wastes all through your body. And your body, your blood, has a very specific set of parameters. It has a very specific concentration in the solution. So a 5% glucose solution, a 0.9% sodium chloride, those are indicative of what your normal body conditions are. pH, your pH of your blood is right around 7.4. It is set at a very particular value for the same kinds of reasons. It's the optimum conditions for your body. Now, with the idea of osmosis in mind, now we can understand why when you're given IV fluids, why your IV fluids are, very precisely monitored for a given concentration. They don't just throw plain old water into your veins. And the reason why is because it's not the right concentration. They give you this very specific combination of solutes inside of the IV fluid so that your blood maintains its normal chemistry. Now, when we give you those kinds of ingredients, when we give you that kind of intravenous fluid, that's called an isotonic solution. Iso means the same. Tonic being from a concentration standpoint. So we've got a similar concentration solution to your normal body chemistry. And as a result, the flow of liquids from your cells to the solution is an equal exchange. No greater, no lesser. If we contrast that with, well, what happens if, let's say that we put pure water into a patient instead of normal IV fluid? Well, that would be an example of what is called a hypotonic solution. Hypotonic solutions have a lower concentration, hypo meaning lesser. So a lower concentration than your red blood cells. The net result is that if my red blood cell is this guy here, let's fix the color here. So here's my red blood cell. There's the dimple on the inside of it. If I have hypotonic solutions here, the net flow of water is I'm going to have way more water coming into the cell than what is coming out. And as a result, the red blood cell is going to swell up. And it can swell up to the point where it actually breaks. And if it does, we call that hemolysis. Because we've got basically too much water coming in to the cell. So that's one scenario. One scenario is we've got our solution and it's not the right concentration. Water flows into the cell instead of evenly exchanging. The cell swells up, bursts, basically dies in the process. The reverse situation, a hypertonic solution. Hyper meaning greater. We have a greater concentration than the red blood cells. And the net result of the higher concentration, again, we look at our red blood cell here. If the concentration is hypertonic, what we're going to see is that water is going to rush out of the red blood cell to try to fix the concentration difference. And the result is that the red blood cell is going to shrink. We call that process crenation. And it's basically the same effect. The cell is going to be unusable and likely die as a result of this crenation, because the concentration of the solution was too high. And so water was coming out of the cell's no longer useful. And the reason why this all happens is because your cells, again, contain a semi-permeable membrane. And the whole purpose of that semi-permeable membrane is your cells need to be able to exchange materials from the inside and the outside. That's how they work. Red blood cells carry stuff to the cells, take away wastes. That stuff needs to be able to be exchanged. So the semi-permeable nature is important. That's how they work. That's why they work. But it also leaves it susceptible to pH conditions, susceptible to concentration conditions, which is why you have to be super careful, super careful about what goes into your body, especially in a kind of a medical application. Last thing that we're going to talk about here in this chapter is dialysis. Now, dialysis represents, again, what happens here in a semi-permeable membrane situation. So again, thinking back to when we were kind of looking at the differences between a colloid and a solution. If we have this membrane bag, again, we call membrane bag a dialysis bag. It's the same idea. If you have that solution in there, what should happen is that as that dialysis bag sits there, the small particles should be able to find their way out of the bag. And the large particles, like your starches, your proteins, the things that would make a colloid, as opposed to just a solution, are going to stay inside of the bag. And so this is kind of similar to the process that would happen in hemodialysis. So if your kidneys fail to function properly anymore and you get put on dialysis, this is similar to the kind of process that would happen where the point of the artificial kidney, the point of dialysis is, since your kidneys basically filter your blood and remove your waste particles from them, if you don't have that, if your kidneys are no longer functioning to do that, dialysis does that for you. And what it does is it uses this concept to remove the waste particles out of your bloodstream, because the waste particles would the urea would get stuck in the membrane. And so you could extract it that way, since your kidneys can't do it for you. Okay, so again, based upon our previous work here, let's go ahead and do a couple of quick views here, some study questions, and then we'll wrap this up. So to answer this question, we have to remember what isotonic is. So isotonic is 5% glucose, 0.9% sodium chloride. So let's just write normal is 5% glucose, 0.9% sodium chloride. And so what we want to do is we want to look for, are there scenarios here that match these? So number 4 here, 5% glucose solution, that is normal. That's isotonic. Everything else, we start to look at and compare. Okay, 2% sodium chloride, that's above. So that's hypertonic. 1% glucose, that's below. So that's hypotonic. 0.5% sodium chloride is below. So that's hypotonic as well. So when we get questions like these, that's the kind of comparison that we need to make is, compare it to normal. Is it above? Hypertonic. Is it below? Hypotonic. Is it at? Isotonic. Same kind of question now. Again, normal is 5% glucose, 0.9% sodium chloride. So now we need to kind of go through and think, okay, isotonic would mean no change. Hypotonic would give hemolysis. And hypertonic would give crenation. So 5% glucose solution, I compare, oh, that's normal, that's isotonic, no change, A. 1% glucose, that's not normal, that's below normal, that's hypotonic, it would be hemolysis, B. 0.5% sodium chloride, that's below also, hypotonic, so hemolysis, B. 2% sodium chloride, that's above. That's hypertonic, so it's going to be crenation, C. So that brings us to the end of the chapter here. And so, again, I recognize this was a long chapter. There was a lot of moving pieces and parts to it, and a little bit of calculation work that you had to bring in with the molarity and the percent by mass and whatnot, and the dilutions. But the thing to kind of remember here with this chapter is that ultimately we're talking about, for the most part, solutions in water. And so looking at what are some of the properties of those solutions, how do we quantify just how concentrated a solution is? We have some words that describe solutions. We have words like strong electrolyte, weak electrolyte, non-electrolyte. We have words like saturated and unsaturated. But sometimes those descriptions aren't enough. And that's where the concentration calculations come in. And it's those concentration calculations that ultimately lead to these other descriptions that we talked about today, where we start to look at osmotic pressure, dialysis, and whether or not what we put into our bodies will actually be safe for our bodies. So I'm going to wrap that here. Have a good day, and I'll see you next time.